Hello friends, in this video I will explain subroutine concept that is used in microprocessor and microcontroller program, but special focus will be on instructions used in 8051 microcontroller. Here that will be the different case, means subroutine is the concept which is actually common in both microprocessor and microcontroller, but the instructions which I will explain is only related with 8051 microcontroller, because I am currently explaining the series for 8051 microcontroller. So here is the concept for subroutine, the subprogram that can be used any number of times by the main program. Generally a subroutine is a program which is actually written outside the main program, and that program can be used multiple times. Okay, so here when same functions is required more than once in a program, it is frequently written as subroutine. So if you want to use some program multiple times, in that case that subprogram should be written outside, and we should call this program in our main program, and this subprogram is known as subroutine. And here is the concept of subroutine. Now note here that this is our main program and it is starting from some memory location. Here it is written as 0011, but it can start at any memory location. Now as it is starting, definitely it will end somewhere. Now note here that it may end to some memory location, let it be 1000. So it is starting from 0011 and it is ending to 1000 H memory location. And if we have to use some program multiple times, in that case we write it as a subroutine program. So you can see here that this is a subroutine program which is written here, which is actually starting from some other memory location. So if we are using 0011 to 1000 H memory location, it must start from some other memory location, let it be a 2000 H memory location, and let it be ending to the 2050 H memory location. Now here is the actual concept. Now whenever we are using subroutine, we will use one instruction known as call instruction, and this call instruction will call this subroutine in our program, or we can say that our program execution will terminate, will jump to this particular memory location, which is nothing but a subroutine. And once the subroutine is completed, it will automatically return back to the next line which is to be executed. Means if we are at the 0013H memory location previously, and after execution of this subroutine, we will return to 001 per memory location. Generally, subroutine allows a program to break down a complex task into smaller and more manageable pieces. So if a lengthy program is there, we can break that program into subparts and we can write this in the form of subroutine. A subroutine is a block of code that can be called from anywhere in the program and return control back to the calling code when it is done. I have already explained it. So we can call it multiple times just like this. Here this program is called once. You can see here it was called once. Once it is executed, the program was written back, but again it is called here, and again the program will execution will move to this particular memory location, and again it will come back to the next memory location which was there before the execution of this subroutine. Now how this process goes through, we will see it. As in subroutine, the program execution is actually shifted to some other memory location. Means the address of this program memory, which is generally stored into program counter, now this program counter is modified to the new address, and it has to come back to the next memory address. and therefore we will require some memory location to store this value of program counter, that is the which is actually indicating the next address whenever it is returning back from the subroutine program, and therefore this is actually stored to some memory location known as stack. Stack is nothing but the internal memory address here, and you can see here that some address is actually stored here, some data is stored here, and this data is actually indicating the address of the we can say that previous address of this program counter whenever the subroutine is actually executing, and therefore stack is used for the register saving in subroutine. The recovery should be in the LIFO format, that is the last in first out. It means that the stack pointer will increase and will save this memory address, and further this memory address is actually restored into the program counter. Now let us see one more concept related with the subroutine, that is the nested subroutine. Subroutine nesting is a common programming practice in which the subroutine calls another subroutine. So here one subroutine will call another subroutine. When subroutine 1 calls another subroutine, let it be subroutine 2, then the return address of subroutine to be saved somewhere. As I have already explained that whenever we are using subroutine concept, it should be the address should be saved somewhere. Here is the concept of a nested subroutine. Here one subroutine is called as subroutine 2, then subroutine 2 is calling another subroutine, let it be the subroutine 3, and whenever we are moving, the program counter is actually modified here. Here it is modified, then again it is modified, then this subroutine is executed, and program counter is always executing, always holding the address of the next instruction to be executed, and therefore it will have this address here, and this address is to be stored somewhere, and this address is nothing but the stored at some memory location which is indicated by the stack pointer, and this memory location is nothing but the internal memory location, and this is actually here follows the format of LIFO, that is last in first out, means first here note that the program counter is first modified here, let it be the first address is 2030 here. Now the second address, let it be 5132 there. So it is just stored like this. Okay, here this one 20 that is 20 is indicating the LSB of the program counter, then this 30 is MSB. Similarly this is LSB, this is MSB, and now program counter is holding the current value, but when it is returning back to the subroutine 2, it will first access this one, that is the address of this program counter. Okay, similarly this 2030 is the address for this subroutine, that is subroutine 1, and first this address is accessed, and later on this address will be accessed, that is 5132 will be first accessed, and 2030 will be accessed later in the sequence, that is the in case of stack pointer. Now two main instructions are used for this accessing to access this subroutine. The first one is call instruction and another one is return instruction. The call instruction is indicated by CALL. Now these call instruction are of two types. Actually in case of 8051 it is A call and L call, whereas return instruction are also of two types. One is RET and another one is RET. I will explain it later, but call instruction simply indicates call of subroutine. Whenever in main program the call instruction come, it simply means that it is the program counter will now move to the subroutine, and once the subroutine is started, that is program counter will actually indicate the starting of this subroutine, first line of the subroutine program. And once the subroutine program is executed, that is it get over, how it is indicated? It is actually indicated by the RET instruction, that is return instruction. And once it is written, definitely this instruction is moved to the next instruction after the call instruction in our main program. So this is call instruction and read instruction, return instruction respectively. Here call instruction will store the value of program counter on the stack, whereas return instruction will retrieve the value of this program counter from the main program and store into the program counter. So overall, I will explain this process again. These are the instruction for subroutines in 8051. It is A call address 11, L call address 16. Now here address 11 is actually indicating the 11-bit address, whereas address 16 is indicating the 16-bit address. And two instructions of returns are RET and RETI, that is return from subroutine and return from interrupt subroutine. So here call instruction are of two types, A call and L call. A call stands for absolute subroutine call, whereas L call stands for long subroutine call. Note here that the memory byte required for A call is 2, whereas for L call it is 3, whereas in case of return instruction only 1 byte instructions are available. So let us start with the first and simple one, that is the L call address 16. So we can write example just like this: L call 5000H. It simply means that the program memory, the program execution will call the interrupt which is stored at 5000H memory location. But actually in case of 8051 programming, we use here some label to indicate this address. Let that label be the next here. Okay. So L call, this instruction is used to call the subroutine. The current program counter, okay, it is PC. I will use PC in my subsequent slides also for the program counter, is pushed onto the stack. Okay, so the content of this program counter, whichever the address actually it is indicating, it is pushed onto the stack, and then the program counter is set to the address of the first instruction in the subroutine. For example, if L call 5000 is there, the program counter will move to the 5000H memory location. Now let us explain this program. Here let program counter is actually 1234H and stack pointer is currently having value 07H, and let L call instruction is there. Okay, and this next label is actually indicating let it be 5000H as previously stated. Now what will happen once this instruction is executed? Now note that I have already explained the procedure. First, this is a 3-byte instruction, L call NXT. It is a 3-byte instruction, and therefore the content of program counter will be automatically added with 3. And here the program counter was having 1 2 3 4 value, it will automatically be PC equals to 1 2 3 7H. Okay, so 3 is added here, and the program counter is modified to 1237H from 1234H. Okay, now stack pointer, which was previously 07H, now it is added with 1, it will be 08H. and as it is written here, the program counter is pushed onto the stack. Now the current value for stack is 08h, and this stack pointer is having first PC lower value, means at 08h we will have value. Previously it was here we are having alcohol as we are having the value for PC is 1237h. so here this is our lower byte. Okay, so PC lower is nothing but here 37h, so PC lower will be 37h. Again stack pointer will increase, means here this 37h is stored at 08h. I can write here 08h. Okay, at 08h we have stored 37h, and now stack pointer is again increased to by 1, it means that 09h. Okay, now at 09h the MSB of the program counter is stored, that is higher byte of is stored, which is actually here 12h. In this way the program counter value, that is 1237h, is stored at 09h and 08h respectively. Further, new address of the PC is actually stored, which is nothing but here the 5000h, and therefore we can write here program counter will be modified to new value, that is 5000h here. So this process is actually executed after lcall instruction. Okay, now next instruction is acall instruction. Note here that the address used in acall instruction is the 11-bit address. Okay, now the PC is loaded with the indicated address here, and the subroutine address to be loaded in PC is calculated by replacing LSB of the program counter with the lower byte of absolute address specified in the lcall and replacing bits 0 to 2 of MSB of PC with upper 3 bytes of 11-bit address. Okay, now let me explain it. Acall instruction, here the address is of 11-bit. This 11-bit address is actually divided into two parts. One is lower byte, okay, lower 8 bits there, and 3 bits which will remain will be there. Okay, now let us assume that the program counter is currently having value 12334h and acall instruction is there. Okay, acall instruction is actually a 2-byte instruction. Note here that lcall instruction was 3 byte, whereas acall instruction is only of 2 byte. Okay, now this 2-byte instruction will increase the program counter by 2 only. Okay, and therefore program counter plus 2, that is program counter will be modified to new value, that is the 1236h here. Okay, now this 1236 is to be stored into the stack pointer. Now if stack pointer is initialized with 07h, it will be incremented to 08h, as I have already explained in my lcall instruction. So here this 36 is stored, and at 09 the higher byte is stored, that is the 12h. Now if this next is indicating, let it be some random value 2300h. Okay, if this next label is indicating 2300h, actually not 2300, it will indicate some 033h because it is only having 11-bit address. Okay, so this lower byte is just copied here. Lower byte of this label is copied here, that is 00 will be just copied, these 3 bits. Okay, now in this case 3 is indicated by 011. So D2 is 0, whereas D11 and D0 will be 11 respectively. Okay, also note that this program counter is some bits, that is 3 to 7 bits of the program counter remains unchanged. So we are having 1236 as our previous address. Now 1 is written in hexadecimal as 0001, and here 2 is also written as 0010. So we will use only one bit, that is 0, and therefore the new address for this program counter will be 1300H. So in this way the program counter will jump from 1234H to 1300H. So the new content of program counter will be 1300H as per ACALL instruction. Now let's see the next instruction, that is return instruction. So return instruction is used to return from the subroutine to the main program. Okay, and this is generally used at the end of at any subroutine. Once we use the lcall and acall instruction and the program counter is modified with the next address, after return instruction we will come back, and here the flags will remain unaffected. In lcall and acall instruction also the flag will remain unaffected. Now let us assume the operation here. Here let the PC is having 3255 and stack pointer is having 09 address. After execution of return instruction, return is at the end of subroutine program, and after execution of return instruction, first the higher byte of the stack pointer. Okay, now we are having stack pointer. I will take the same previous example. We were having 07H, 08H and 09H in our program counter. Okay, now here the stack pointer was increased to 08H and 1234H was actually there. So 34, that was the lower byte, and 12 is the higher byte. Okay, now this higher byte of stack pointer is just copied into the program counter, and therefore from 09H this 12 is copied to the program counter's higher byte. Okay, program counter is actually of 16 bit, so higher byte is counter. Now stack pointer is decremented by 1. So from 09 we will move to 08H, and at 08H you know that here 34H written, that is the lower byte of the program counter. Okay, so here programs counters lower byte is 34H, which is actually copied from 08H into the stack pointer, and again stack pointer is decremented by 1, means previous position of stack pointer will be there, that is stack pointer was previously indicating 07H. Here also stack pointer will be 07H at the end of return instruction. Now next instruction is RETI instruction, that is the return interrupt subroutine. Okay, now this instruction is identical to that of return instruction, that is I already explained. With operation, the same operation will be there, only change is there, that is this instruction is used to return from the interrupt service subroutine. Note here that it is used for interrupt service subroutine itself. Interrupt service subroutine is a program which is written for the interrupt request. Okay, if you don't know anything about interrupt request, note here that interrupt is the signals which are used by the some external devices for 8051 controller to stop the, or we can say that to halt the main program. So it is the interrupt service subroutine, which is the program which works on the interrupt signal. Okay, once interrupt signal is there, we will use the RETI instruction. Further, the process for RETI is same as that of return instruction, same will everything will be just same. Program execution continues at the address that is copied by the stack. No flags are affected. Okay, remaining thing, everything will remain as it is, only it is used for the interrupt service subroutine.